Hello, good afternoon. My name is Stephen Voelker. With me I have our team leader, Sorelle, Veigne, and team member, Owens. Together we are Team 3, CAG Tuning, and the title of our project is Implementation of Auto-Tuning in an Emulated Bioreactor. Our faculty advisor is Professor Charles Nippert from the Department of Chemical Engineering, and our project coordinator is Professor Victor Marcus from the Department of Civil Engineering. So a little bit of introduction about what we've been doing. We've been using a feedback loop process. So if you follow the mouse on the screen, you can see we are introducing a set point as the control variable into a PID controller, and that stands for proportional interval derivative, and that will generate a manipulated variable which goes to our physical process, and that physical process will generate an output that is then looped back to the set point and compared via an error function. So as you can see here is our physical equipment that is down the hall in this building. Right here is our pneumatic valve, which we are controlling. We control the stem valve position of this valve, which is then connected to our two interacting tanks. The first tank is for first order systems, and the second tank is for second order systems. And these tanks interact by a valve in between them. And also, at the bottom here, you can see another pneumatic valve, which is our outlet valve. So basically, we've been using tuning, which will bring our control variables back to the set point in case of any disturbances or nonlinearities in the system. This will maintain stability for the process. However, auto-tuning, more specifically, is this process automated completely so that a control personnel will not have to operate a computer all day for this process. And to generate our auto-tuning, we conduct relay feedback tests, and these tests will provide more control information from the feedback loop. And what we do here, as you can see, our pink square right here is the height of the valve position, and that is a wave generated manually by the user, and that in turn controls the height of the water in the first tank, which you can see in blue as the sine wave. And from this sine wave, we can calculate the gain and the period of the system. So normally, we insert the change in the loop and note the response and use this response to calculate our controller settings. However, these normal tests do not take into account systems with dead time. And what dead time is a delay in the signal from the process to our controller. So therefore, we've been using methods by man named Luyben. So his methods are suitable for systems with dead time because they give more control information for the system. And as you can see here, the shape of our curves tell us what type of system we're using. The square wave at the top is for systems with very large amounts of dead time. At the bottom, we have a triangular wave, which is for very small amounts of dead time. And what we've been seeing and using is this curved wave in the middle for a moderate amount of dead time. So therefore, we can calculate the curvature factor, period, and the gain. And a little bit about the methods we've been using. We've been using very common Ziegler-Nichols tuning methods, and also IMC tuning equations. And the new equations we've been using are Tyreus-Luyben tuning equations, which are really just a variation upon the Ziegler-Nichols equations. And you can also notice that the derivative portions of these equations are not present because derivatives, they generate more noise in the system than is necessary, so we set them to 0 and do not worry about them at all. I'm going to pass it over to Charles for our project goals.
Okay, these are the main goals of our project. First was to design a controller and user interface for the two-tank system that we have down in our chem engineering lab, and then to make it so that various algorithms could be used to tune that system using a PID controller. Second, we wanted to take that system and then make it emulate a bioreactor. And finally, we wanted to test the system and validate the system, make sure everything is up and running. Right here, you can see we have a more complex version of our process diagram. We start down here with the set point, which is input into the auto-tuning controller. And then that you have to add dead time because our system does not actually naturally have any dead time in it, but the equations we're using rely on systems with dead time, so we have to artificially add dead time, which essentially adds a lag between the auto-tuning controller and when the height of the valve is actually changed. So then from the dead time controller, the signal goes to and changes the height of the valve, which in turn changes the height of the two tanks, which below here and here you can see the equations for those two tanks. And from the two tanks, you get a final output height, which then in this feedback loop here is compared with the original set point, and then the system automatically determines whether it needs to increase or decrease the height based on the comparison between the set point and the output. Okay. This here is the typical output for a fermenter. You can see it has a nice curvature, which allows us to use, being its first order plus dead time system, which allows us to use the Luyben equations to for this system. And you can see results from the Luyben equation over here, and therefore we can use those to plug into our system and then therefore allow our system to emulate a bioreactor. This is the graphic user interface that our system uses. It's abbreviated as GUI. Over here you see the faceplate, which you can input values, and then the system can also calculate and give you back certain other values. Down here, you choose the tuning method that you want. Below that, there is the sine wave generator, which is hooked up to this output valve here, and you can have a sine wave function control the output valve. And then there are tank 1 and tank 2, which the heights displayed on the GUI are equivalent to the actual heights of the system. Now I'm passing over to Sorelle for planning and management.
Thank you, Joe. Here is our schedule that we followed for the project. We're using existing equipment, so we didn't have to buy anything or install anything. So most of our time was spent on testing and evaluation. And during this time, we also had reports that were due. And as a matter of fact, our paper was accepted in the International Journal of Engineering Pedagogy. Our budget was $300. We only used about $100 for our postage, and so we were well within our budget and also on time for our budget. A significant portion of our time was spent on designing a process flow sheet, which is what you see up here. This process flow sheet is basically a code that the process follows as it controls the system. So the signal comes from the top right here, and this loop initiates the system, and this loop right here collects the data. This one right here collects the curvature. This one calculates the setting based on this tuning method and takes them back for the system to make adjustments. So here are the results of our first order plus dead time test. And this is basically a feedback test, as Steve explained before. And as you can see on the diagram, the step one was initially at 15 right here. And when the step one was changed to about 25 at that point, the system adjusted to those changes and moved to that set point. Also, when the control valve, which is this line right here, was moved, was opened to 100%, the system didn't destabilize and it maintained that set point. We also switched tuning method from Tyreus-Luyben right here to Ziegler-Nichols, and the set point, as we expected, maintained the set point. We had an issue with the IMC tuning method, because when we switched from Ziegler-Nichols to IMC, the system would adjust and it moved to a 0, as you can see from here. So we also did a second order just for trying not to say. And this wasn't really part of our project, but we wanted to do it so as to verify if the autotuning would work. So what you see right here is the stem output valve. This is basically the sine wave generator that was connected to the output valve. So here the set point was at 25. We changed it to 30, and the system stayed at that set point. Even when the sine wave was turned on here, the set point was maintained. Changing tuning methods from Tyreus-Luyben to Ziegler-Nichols still kept the system at its stable point, and the system maintained its set point. We had the same issue we had with our first order testing. The IMC moved, the gain was moving, the set point was moving to 0, so that it worked for our system. So how significant is what we have done? So basically the fact that we were able to seamlessly switch from Ziegler-Nichols to Tyreus-Luyben, and the fact that the process was able to maintain its stable points even when there were perturbations like the opening of the valve or the changing of the mixer point is really important especially in industrial settings where processes have to be maintained at a set level. Also, by simulating this bioreactor, we can apply the same principle to other processes, both biological and chemical. Now I'll hand it over to Steve for the.
So, from our tests, we've concluded that our system is able to respond correctly for a bioreactor process for first and second order plus dead time. And it has a distinct curvature factor, which is predicted by Luyben in his papers. And also, our controller can seamlessly transfer between different tuning methods. And when I say seamlessly, I mean you press a button and it'll change for you. And also, our results both from first and second order show that Tyreus-Luyben's equations give better control than Ziegler-Nichols, so they're more optimal to use. I'd like to thank you for your time and open the floor for questions.
Do we have any questions for this group? Start over there.
If you're running a fermenter, are there any like significant parameters that you're going to have to control, like that are more important than others?
Well, for a fermenter, a very important aspect would be the temperature, because it would be able to change the rate of the rate of the reaction. So that would be one thing we want to monitor.
Other questions? Thank you very much, guys.